Hi guys, we will apply the same sampling method in order to estimate the area under the curve. So in this case, we have this function. I'll show you the function later, but we know that we have to estimate the area or the green area here, and then the rest is not important. So the red one is uh, not consider. Okay, so this one, the green one, I mark it under, and then the red one I will mark it over the curve. Okay, so the function will be this one, sine over x, and I will, in order to draw this picture, I will need to draw the x from -20 to 20. So you can see here x from -20 to 20, and then for the y I will draw from 0 to 2, which is above here, 2 here and 0 is here. Now you cannot draw, this is 1. 1 is the biggest number of the of this function, so you cannot draw below 1. So 1 is okay, but if you draw below 1, so for example, let me give you an example of 0.7, and I will see there's something wrong with this 0.7. There's something wrong with the picture. Okay, so you can see here there's a cutoff area, so there's supposed to be more area in on top of here, this picture, but because you lower your upper bound of sampling, then you lose the area on top of here. So if you want the most optimal one would be 1, but I will give you a 2 or 3 in order to show you that actually it doesn't matter so much on this part. It just like when you give the big upper bound like this, you have to reject a lot of samples in this area, and then it wastes a lot of your computational resources. Okay, so let us go with this picture, and now I need to estimate the area under the curve here. Okay, so I use the same rejection method, meaning that under the curve I will keep, and then above the curve I will reject, so it will go like this. So the first thing I will use the red K, which is the uh, green area under the total, which is this one. The green area is just that the part that we want to estimate. So I will call it, this one is I for integration I had, which is what we want to compute, and the other one, the total here. Now the total here can be computed easily, right? Because you know that this one is 20 minus 20, 20, and then this one is over 2 already. So basically you can just sorry, this one I want to give, give specific number for this one, so you know that it cannot be a general number. So I had from minus 20 to 20. Okay, so you know that this is the you need the upper bound or lower bound and the upper bound for this integration, not like from infinitive to infinity. So this the one below will be computed by 2 multiplied by the 20 minus minus of minus 20. Okay, so this will give you 40, right? 40 and 80, right? So this in total will give you 80. 40 and then 80. So this is just we just compute from the figure from the picture, right? And then the other one is we compute from k hat, which is from our samples here. So we have the green sample, green dot or green point, the count of green dot over the count of all point dots, and then this one will be so if you want to count this one, I will give you the number in our script. So it will be GDF under, okay, and then over the total of the row in the GDF, okay. Now if you bind those two parts together and then you have this thing here, and then equal to this thing, and then if you take the 80 over here, and then you will get this answer. Okay, so this one will be 80. 80. So if you want to generalize this thing, then it looks like this. Hat A, B, and then M, which is M, which is upper bound. Maybe I will call U. Upper bound of the picture multiplied by B minus A, and then this one. So this is the general solution. Then this one is the for this our picture, our case. Okay, so so you see that this estimate I had is will depends on three things: the A, the B, and then the U. So if you lower the U, and then it will lower your score as well. And then sometimes it's go wrong because you just cut off the top of those peaks or the mountains. Okay, so let us apply this computation in here. So I will call I at to n row of the JDF under. Actually, I can copy the whole thing. Times, and then that's it. But then you need to select this GDF under, which is this thing, under, and then that's it. You can display this one with the title as well. So basically, looks like this. And then okay, let us see. Okay, this is about 4 something. I cannot tell, to be honest, I cannot tell this number by this picture here, because the boundary is it just between 4 and then between 20 minus 20 and 20, which is the random number. So but then I can test. So if I make it from 0 to 20, it have to cut down by a half, which is about 2 point something, right? So so I will trust my method like that. Okay, so let us go from 0 in here. So from if you go from 0 from here, then it doesn't go with 80 anymore, because it's now for it will be 2 times uh, 20 minus 0, 0. So it will go like this, and then later I will show you how to do the, there you go. So it dropped by 2. So this is the area that we try to multiply, to estimate. Okay, so now I show you how to make the general with the parametric version of this. So I will give a to uh, a here. Okay, so a will be 0 and b will be 20, or maybe I will do 15. So a will be here, b will be here, the upper bound u will be uh, 2 in here, and then the upper bound go into here, and then this one will go u, b, and a, and then hopefully it will go, everything will go. Okay, let us start with 20 first, and then see it produce the same thing or not, and then later we change to the other number. Okay, so due to randomness, sometimes you have the different number. If you want to fix the random picture, it's still random, but then it's fixed with number, then you just set the seeding number into a fixed number, like 1 2 3. Okay, so it will give you for each seeding number, it will give you the different picture and then different number as well, but it's roughly is about 2. I will go back to 20 to minus 20, and then hopefully it will put you 1 7, like that before, right? So minus 20 and then 20. Yeah, so you have 4.25 now. So when you raise the number point in here, it will also produce a better estimate, hopefully, for this integral. Okay, so this is the general function for this case as well. But if you want to make it like actually a function, then you can uh, like subject, which is function, and then I'll give you the whole thing in here from here. So n will be like this, a will be like this. So you have to uh, turn those guys into the function parameters, and b like this, and then u like this. So if you want to change this thing, you can also do in here, function equal to, and then you change this one to function. And I will give some indentation in here to make sure that we have a, okay, I return g, and then there we go. I will repeat this experiment with two of them, and you can see. So g1 equal to the test subject of I will give the first one will be from a from 0 to 20. Everything else is the same. And then the second experiment, I will give the one from minus 20 to 20 to 0. And because I know that this one is symmetric function, so I expect those number will be roughly the same, right? So grid range growth equal to a list of G1, G2, and then I want to compare this one side by side, so n code will be 2. Therefore, it will take the two functions side by side, two cases side by side. What's wrong with this thing? Let me see. Sorry, I think I don't need this one anymore. Just now I draw everything in the same picture, but then I think we don't need those guys anymore. Then we just, sorry, this one I have to specify B as well, otherwise it will get lost. So I have to specify the two parameter, otherwise it won't produce the pictures as we. Okay, so there you go. So you can see here this one from 0 to 20, and they give me 2.3 before, and then this one from minus 20 to 0. You can see these guys are symmetric. Maybe I will switch the number 1 and number 2, and then you can see it will be better for you to see the pictures, because it look like a little bit, yeah, symmetric to me at the moment, because this one go from 0 minus 20 to 0, and then this one go from 0 to 20 to half of the picture. Actually the numbers are quite similar. Okay, so if you want to lower the bound, so this one is 20, this one is 2, you can lower this one to maybe 1.1 as well, so you can lower the two part of the thing. So u equal to 1.1, and then here you also u equal 1.1, and then this thing. So this is the picture. And then the other one, which is you can change this function into any other function as well. Let me change the second function. This is the first function. The second function, I will use this one. Uh, 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 I will call this one cosine 2, which is also the function cosine, which is also symmetric function over the, I think, yeah, over the y-axis, and then I change this one to, if I want to do this one, I will change function in equal to my cos to changed. There you go. So this one is a periodic function, right? So you can see a lot of thing going on in here. So a lot of intervals going on in here. But then eventually you can give this one over 10. Yeah, so that's about it. If you want to use sampling method to estimate the area under the curve, this is the framework for you to do it.